you're in charge. I was prepared to talk a bit about behaviors. Wasn't there someone else who
Okay.
wanted to say something? Was someone else? No.
No, we didn't have anything else
Okay.
planned at least. Yeah.
Yeah. So this is again in a continuing series of like get our heads together and bang them against the wall for a while and see if we can figure out what's going on. Um, that's how the research seems to go in this business. So last week we also talked about behaviors and the way Niels was presenting it was it's a very different way I think about it, and that bothers me because I think we all need to be thinking about these things the same way. So I wanted to go back and just go through again how I'm thinking about the problem, and starting with some basic assumptions, um, and just working through it and making sure we're all on the same page. At least we all understand what I'm trying to argue. Um, Before we can, say it's right or wrong or anything like that. Because I still think there's probably a lot of confusion and lack of understanding in some of the concepts here because they're quite difficult. It takes time. So I feel like it's good to go back and review this stuff. Here's Vivian. So unlike everyone else here who's really good at putting together presentations and making them look really spiffy, I only wrote up some text. Not because I'm refusing to write up presentations. It's just I've been extremely busy these few weeks. I have a lot of things going on in my family, and health issues and so on with my kids and so on. So just don't have all the time I want to have on this. So I'm going to walk through. I have like one very simple slide, but mostly just text, and I'll walk through it. We just discuss them. I guess I will share my screen, and you're going to look at my Word file, and that's I'm finished apologizing for that. Let's see here. Okay, I'm going to share this one. So hopefully you can all see that.
Yep.
Okay.
Yes.
All right. So I started off with background assumptions. These are just remind us all some of the things that we assume. That I'm viewing this completely from the neuroscience point of view. This is not a Monty presentation. So we have to bear that in mind. I don't think about Monty as much as I think about neuroscience. So that's my area. And so I started off some background assumptions. I want to go through them. We all should know these already, but in case you don't, just speak up. I'll go through them quickly, and then we'll jump into the object behaviors, which starts at the bottom of the screen here. So it's really, I mean, I think about all these problems under these sort of images of these columns and the layers and the cells and the neurons and synapses. And so I'm not sure everyone does. I'm pretty sure most people don't. Some people might, but it's worth going through it again. So the basic idea is that columns learn models of things in the world. You can see my cursor here, I assume, right? Models, and we associate basically observed features with locations in space, and we do that through moving. That's how we build up models. Part of the models are we have to learn the orientation of the feature independently of the object ID, which is something we didn't know in the beginning, but we do now. We think the orientation encoded via mini columns, that's an hypothesis, seems to be fit V1 and a few other places, but it's not necessarily 100% certain. I've come to believe that all models are compositional. At least that's the way I want to think about them. All models are composed of other child objects. So I really we want to banish the word feature, or at least understand the feature is more than we typically think of it as. So if the feature or the child object comes from a sensor patch, then the child object is very limited. So the way I think about even a column in V1 is basically learning compositional models, but the inputs to it are coming from the sensor, and the sensor patch can only recognize a certain number of things. So there's a limited number of child objects there, and that's just the way I like to think about it. Even V1 is learning compositional objects. It's objects composed of other things. And of course, if the feature in the child object comes from another column, then it represents a more structured object like the other column can learn. So the logo on the coffee cup. And any individual column, although it's learning a compositional object, it doesn't really know what the inputs represent. A column doesn't know if its input's coming from one place or another, or what it means. And so it's just saying associating some SDR with the location. But through the back projections, a column can basically say, well, at my location, it tells the child, you should be observing this. And these are just learned associations. The parent object doesn't know it. It's just sending back saying, well, we both observing these things at this time. Of course, locations are defined within a reference frame. We often use the word reference frames of metric properties. This came up last week when we talked about sort of the changes in reference frames. To me, I'm not sure what the technical definition of metric is, but for me, metric means that the spacing between the locations is the same in all directions. It's consistent, or I should say the same starting at any point. This, of course, this gives us these really nice properties. You can path integrate from any location in any direction and end up at knowing where you're going to be. And it also means you can calculate the distance and direction between any 2 points. So generally, reference frames can't morph or change without losing their metric properties. Although, as Niels pointed out last week, grid cells do this too a little bit. And it's kind of a mystery, but they don't do it a lot. They just do a little bit. And it's been studied, as far as I know, no one understands it. It's not like the total thing is lost. It's just like it gets slightly distorted in certain situations. So we know that in the brain, reference frames are created by grid cells, but it's not just grid cells. Bear in mind, when we talk about grid cells, there's a whole series of other cells that have grid-like properties. People talk about grid cells because they're the simplest ones to understand, but there are actually lots of them, and people are confused by that. Other types of cells. So there's a lot of things not understood about how they work. One being, we've talked about this quite a bit, they appear to be two-dimensional. And I have all this evidence why grid cells are two-dimensional, but we would like them to be three-dimensional. Okay. And then the same idea, grid cells on themselves do not represent any unique locations. The grid cells repeat over and over again. That would be true for any neuron unless you have grandmother cells. So it takes multiple grid cell modules or grid-related cells, they don't have to be grid cells themselves, to create unique SDRs that are unique to the object and the location object. And then it's well understood that when an animal recognizes a new environment, the grid cells re-anchor, meaning which cell within a grid cell module is active. And if you have enough of these, then you essentially define a new set of locations for the new object. So it's always important to think when we talk about locations in the brain, it's unique to the object. It's not, and yet they still have these nice properties of path integration.
Can I ask a question real quick?
Yeah.
So the re-anchoring, from what I recall, there's like the idea is that it's sort of random. There's like a random initialization for the re-anchoring.
Well, no, we don't know. It appears to be random from a neuroscience observation point of view. There may be some underlying mechanisms that no one knows about, but there's no random number generated in the brain. But so the assumption is that you can treat it as random, which cell becomes active.
Do you recall off the top of your head whether if I put a rat in environment A, it's got its anchoring, then environment B, new anchoring, then back to environment A. Do you recall if the familiarity of the environment helps re-anchor in the same way?
Yeah, obviously, yes, of course. Obviously, once the animal sees enough of the new environment to know where it is, then the cell is re-anchored. It has no other way of knowing, right? Other than through some sort of observations. It could be smell. It could be tactile touch to the whiskers of a rat. It could be things they see. Any set of clues that now lets the animal say, "Oh, I know where I am." That's when the grid cells re-anchor.
Right. I was just wondering if it would re-anchor in the same way on repeated.
Absolutely. Right.
Okay.
That's the whole idea. And it's one we're relying on essentially that when you come back to the same environment, in our case, come back to the same object, that the grid cells would re-anchor exactly the same way, and therefore you're back in the space. Once you're in a particular object space, then all the predictions can make sense. Like then you know what to expect at every location. So it has to re-anchor to the same set of anchoring points for anything to work. And that's what's observed, if I understood your question correctly.
Yeah, that's good. I was just thinking about the random initialization thing and how that would be a problematic issue.
Why would it be problematic?
If we are, say, doing object recognition, like we extend this out to the world of object recognition, we think, well, we definitely would like to be able to return to the same overall space when we
Yes.
when we recognize an object for the second time.
Right.
However, like I guess in the very first use of CODs of encountering an object for the second or third time, we haven't fully recognized the entire object.
Well, if
So,
you haven't recognized it, if you're not certain where you are, then they haven't re-anchored. Um, I think there's a lot of evidence for rats in environments on this, and my recollection is, when a rat's in an unknown environment, if someone else knows this, correct me. I think it's not random. I think there's sort of like a I don't know. I had this impression there might be sort of some, background, like unknown environment in space, but
Yeah, I can't remember what the result was. I just remember there was a study, I think from the Moser group, where they put rats in like dark rooms where they couldn't see things. So it's like the
and
animals kind
what
of
and what and did the grid
yeah,
cells always
I
anchor the
need to
same
remind
way?
myself.
The question is, did they always
Yeah,
anchor the
good time.
same way, or was it random? I think they always
Right.
anchored the same way. And also, I think it was also some other interesting little tidbits, which are maybe very misleading. It's sort of like the spacing between the grid cell findings was larger, slightly larger, and then when the animal recognized the environment, they tightened up. So it was sort of like the space becomes kind of looser when they don't know where they are. Maybe that helps them infer. I don't know. There's a lot of weird stuff that they don't understand about grid cells. But this idea, Will, this is really important. That once you recognize an object, once you know where you are, once you know what you're seeing, it's like the aha moment. Oh, I know what this is. That's the moment the grid cells re-anchor. And at that point, then all your predictions come true. Like if I was in a dark room, I couldn't really see things very well. I didn't know what room I'm in. If someone just dropped me in some room, but any one of these rooms that I know, and it's dark, and I'm searching around, I'm kind of confused. And the moment I say, oh, I know what this is. This is the bathroom. Then instantly you can visualize the bathroom and you can know where everything is. It's that crystallization of the grid cell modules re-anchoring that then defines every other thing in the environment. And so we're basically saying things happening in the column.
And yeah, I guess just to kind of close the loop, maybe on Monty. So like in Monty at the moment, we would like start with a hypothesis space where we test like multiple ones in parallel until we know like which space we're in. And so like I guess the question in like biology is there somehow like sort of a multiplexing or like simultaneously encoding of multiple spaces that could be possible until we converge to the true one? Or as I think you were kind of alluding to, Jeff, is there some sort of like background generic space that is used to kind of path integrate through multiple hypotheses until again we kind of
Well, I'm
converge
not
on the
sure if
true one?
I'm not sure if it's passing on through multiple hypotheses. Um, yeah, I think we don't really know the answer to that question. I mean, it's a legitimate question. Brains clearly can do this. We have proposed one possible mechanism, which is the union of SDRs is one way of maintaining multiple hypotheses. That works up to a certain number, and it may be sufficient, and that may be how the brains do it. But there might be other ways. So I don't know. Okay,
The
Will, is
doesn't
that?
seem to be happening with like before the grid cells re-anchor. It's not like there's a denser firing of grid cells, is there?
No, I'm not. No, it doesn't seem to be that way. But it could be. Right, right, right. Again, there's a huge amount of literature on grid cells, and there's a huge number of things that are unknown about how they work. So I feel like if we want to have a more in-depth discussion on this, I would have to spend a week reading papers, something. But we do know they exist. We know these other cells that are grid-like exist. We do know that they re-anchor. It is our hypothesis that, not only, it wasn't our hypothesis, but other people hypothesized, and we adopted it, that multiple modules, grid cell modules, would lead to unique encoding of space. And that it's almost necessary, because if you didn't do something like that, then you can't even encode any space. And I think at this moment, we have to sort of say there's a lot of things we just don't understand about the details. Okay, can I go on? All right. So this last paragraph here basically says we've modeled this successfully so far in Monty about how to learn models of static objects. And of course, what we're trying to do now is understand how to model objects when they're not static, when they change. And we've used multiple examples. We used a stapler a lot. I've used a traffic light a bunch. There's all kinds of objects that exhibit behaviors, your computers, your keyboards, tons of, so many things. And when we say they exhibit behaviors, it's the same object, but things are moving, things are changing on an object. And so we have to be able to learn a model of how, not just the static components of an object, but how it moves, how it can things. And even the simple thing like the staple has many different behaviors. There's the lifting the lid, there's opening up the internals to get access to the staplers. There's the little rotating deflection plate on the bottom. There might be a little catches to open the springs and so on. So, and we have to learn all this, and these are all part of the same model of a stapler. So we're trying to extend our column model to learn how objects can change over time. And then the thing was, there's a couple of it was surprising sort of insights we had along the way. One is that pretty much everything about a model could change. I could come up with examples where the features move, where the features change orientation, where the features change scale, where the ID of a feature at a particular location changes. And these can occur in singular and combinations. And so I say all these types of changes could occur at one or more locations. And so pretty much everything about an object can change. They typically don't all change at once, but there seems to be no limit to the type of changes that objects can exhibit. And this led to the idea that, well, what is an object if everything can change on it? If all the features in those locations and orientations can change, what defines it? And the answer is two things. One is from this I deduce, well, one of the reasons I deduce the fact that the anchoring of the grid cells for a particular object will not change, even if the object changes. We can prove that. And what was the other thing I was just going to say? Also, these changes, of course, occur sequentially through time. I mean, if I saw an orange sitting in front of me on the table, and I walk out of the room and I come back an hour later and there's an apple there, I would make no assumption that the orange turned into an apple. But if I was sitting here looking at the orange right in front of me, and while I'm looking at it, it turns into an apple, I would say, holy cow, that orange turned into an apple. Magic is happening here. So these things, the proximity in space and proximity in time are important for us to realize that this is the same object. And of course, if I just see a small change to an object, if I'm looking at a traffic light, and when the red light turns to green, I wouldn't think like, oh, that's a different object because it's almost all the same. But it is important to recognize that there can be enough changes to objects that sometimes you wouldn't necessarily know they're the same thing. But it really helps that these changes occur while you're observing it. In fact, it's important, and they're close in time. All right, so that's basically defining the problem space of object behaviors, and so we have to extend our models to include that. So here something I already talked about. I propose the anchoring of anchoring of reference frames defines the object. And if the reference frame is, if it re-anchors, then we perceive it as a different object. Therefore, object behaviors are change what is associated with one or more locations on an object. So basically, to learn an object behavior, we have this reference frame with features on it, and now we have to say, oh, under certain conditions, the features are different in different locations, and so on. It's important to remember some objects exhibit no behaviors, some exhibit a few, and some exhibit many. I just talked about an object completely changing to something different. I don't need to go through that. These changes, another thing we used to talk about, like the stapler, what is the state of the stapler? It's open and closed, but the stapler has many states and they're independent. And this can be true for a lot of objects. So multiple changes can occur independently, or they can be causally related. For example, the staple example, I said, well, typically when you raise it over the top, it doesn't change the deflection plate on the bottom, but you could build a stapler when you raise the top, the deflection plate rotates. That would be perfectly okay. And I could easily learn that. So it just says that an object can have multiple different changes that some are causally connected and some are not. And so we have to be able to accommodate that. These are all things we have to be able to do. Often the behaviors consist of a sequence or time series of changes to the object. And so that could be along a trajectory in space. So that would be, for example, the lid of the stapler rising and going down. Sometimes they can turn at disjoint locations. That is, an object can change here or there. I was thinking about traffic lights. And in terms of traffic lights, the lights generally go in the same simple order, you know, red, green, and blue, red, green, and yellow. But there's an old game called Simon. Some of you may remember, it's a kid's game, where it has a bunch of yellow colored buttons. And the whole task of this is to remember the sequence which those things light up. And it's much harder to do that. So, but things can change randomly. But it's not, but generally we like to, it's much easier when we see something moving through space continuously. And then this is the key insight a while back, is that when we learn objects' behaviors, we don't forget the rest of the object's model. So I don't forget anything about the stapler when I've learned that the lid goes up and down. Excuse me for a second here. Okay. So this is sort of the proof to me that the reference frame has to remain anchored, because if you change the reference frame, then all learning is lost. So essentially, we have to, within the same reference frame, we have to have ability to say at any point in time, under different states, what features are we expecting to see where. I got confused on this topic, object states versus current state. I was using the word state for two different things. And I think it's just, I'll just point out my failure on this. I suppose this could go into our wall of fail, perhaps. And then we use the word state for two different things. One is the different ways an object can behave. So I could say the stapler has multiple states. So like I say the deflection plate can be in one or two different positions. Those are different states of the deflection plate. But we also use the word state to refer to its current settings, which is not part of the object model. So the object model has to represent how the top can move and how the deflection plate can move in its different positions at different states. But we can also say, like, oh, what's the state of the stapler right now? It's open. Well, that's not part of the model. That's a temporary condition that we might want to remember. So I don't have a good answer to this question, but I was getting confused sometimes because we're using the word state for these two different things, and they're quite different. So maybe somebody, you know.
Yeah, that's a good point, because we will probably run into this confusion more in the future as well. Because in the Monty implementation, we actually call the message class that we use to send information between learning modules, we call it the state class. So it's like the hypothesized state or the goal state, and so I guess it would be good to think about how we can distinguish the two in terminology, maybe having the behavioral state and the current state, or I'm not sure what
right. Well, that's
word would be useful.
That's here, I started trying to say, oh, maybe I'll use the words behaviors of an object. And then I didn't want to redo the whole document. I just know it. So it's something we have to come to grips with, and maybe we can define some better language for it.
Yeah, like behavioral state and object state. And behavioral
even that's confusing. It's even confusing. You might think the behavioral state the current state of it, or the things that the object can do. So I was using the word behaviors. I could say the object has certain behaviors, and that's not a state. That's like okay, these are things it can do. Where the word state typically refers to a temporary condition. You know, what is the current state? I don't know. I don't think we have to solve it here. I just think it needs to be. If someone wants to come and propose something, it's fine, or maybe I'll do it later. So sometimes I say here, sometimes I refer to these as objects' behaviors, which is clearer than the object states. So object behaviors doesn't have that confusion. This is all about this. This paragraph here is essentially says we have to be conscious of this, because it turns out to do anything interesting, that the system almost certainly has to remember the current states of an object, its current configuration. So if I'm going to do, you know, Niels also talked about making coffee. Well, you know, the coffee maker has different behavioral behaviors it can have. And as I'm making coffee, I have to remember where it was last. You know, was the lid up or down? Was the coffee in or out? You know, was it on or off? Was it plugged in? I have to remember these things. even though I turn away to, you know, I take the coffee maker out and put it on the counter and I go get the coffee. I have to come back. I have to remember, did I plug it in? You know, did I turn it on? I mean, so there needs to be sort of episodic memory to solve any kind of interesting task. And we haven't, to this date, really dealt with that. In the brain, it's almost certainly this is done in the hippocampal complex, the episodic memory. It almost certainly wouldn't be done in columns themselves, the individual columns in the cortex. It doesn't mean we couldn't do it in the columns in the cortex. I mean, in Monty, we can do anything we want, but I just point out that, okay, this is something we haven't really dealt with before. And we will have to deal with it to solve interesting problems. We'll have to have some way of remembering the state of all the objects that we just recently dealt with so that we know what to expect and we know what has to be done next. Okay, does that make sense?
I guess just to clarify, how is that different to us remembering the recent locations and orientations of objects? I feel like that's kind of the same class of problems.
It maybe is. Do we do that?
In a sense, but yeah, I guess in the past we talked about that we can have like learning modules that very quickly build up temporary graphs. That's a bit more like the hippocampus.
Right.
And we talk about it in terms of states, but just in where things are relative to us.
It may be exactly the same thing. I thought about that. I was thinking going back to the dinner setting type of thing and trying to understand that. That's kind of like a temporary configuration. I mean, you know, maybe that I got really confused by it, so I didn't bring it in because I couldn't make sense of it. But it might be the same thing, Vivian. I don't know. Okay. Maybe you can solve it the same way. I don't know. I went on. I didn't deal with that any further. So the next big thing here is, and this was like a really big insight when it occurred, and I've talked about it in the last few weeks, that that I believe that these different behaviors, the behavioral states, if you will, of an object have to be learned on a location by location basis. It's not some, first of all, it's not some global thing. I can't say what's the state of the stapler. I could say, what is the position of the stapler top, or what is the position right now of the flexion plate? But it's not a global thing. And even then, the way to think about it, the right way to think about it is on a location by location basis. This is still a little bit conjecture, but I think it's gonna hold. And it's very similar to how we had the same breakthrough for doing compositional objects. The only way to think about it is not like, oh, it was wrong to say, where is the logo on the cup? That was the wrong way of phrasing the problem. The way to phrase the problem for a compositional object is, at this location on the cup, what is the child's object orientation and scale at this location? And another location, the child's object location scale could change, or maybe not change, but it's on a location by location basis. And I think that's where we have to think about behaviors of objects. On any location, that location can change what it was from what it was before. Before, I would have said there's some feature at some orientation scale, and now I might say there's nothing there, or I might say there's another scale, or a different orientation, or a different feature, or something else, you know, but on a location by location basis. And that seems required to solve a whole bunch of problems. So to do this, I propose that a column has a layer of cells that represents the current. It has a layer of cells because that's how neurons represent anything, right? A layer of cells, kind of mostly, not completely, but usually. That represent the state of the current location. So as I move through the points in space, this other set of cells would say, okay, what should be right now, what should you observe at that location? Because at one moment you might observe A, and another moment you might observe B at the same location. That's the definition of a behavior. And so we need some way of telling if this is a column like layer 4, we have to have some way of telling the neurons to predict something else. At this point, I'm going to switch to my one slide, and I'm going to share again. I shared just that one thing. I'm going to share everything here. And then this is a PowerPoint slide. Hopefully you can see that.
Yep.
Okay, this is a very crude idea here. Typically, we talk about layer 4 as the input for the feature from, a child object feature. Layer 6 is going to be representing a location. And in basic, our model today is you basically you form a unique representation of the feature at that location in layer 4. The idea is that there'd be another input to layer 4. And I just picked layer 2 just because I needed a placeholder. I actually didn't go back and look at what would be a good candidate. So just consider a pure placeholder. I have no idea if it's where it is. But the idea, there's another set of cells that are representing state. And so the three of these together combine to tell you what. So at some location, based on the state, you would predict one feature, but based on a different state, you would predict a different feature or no feature. And so this is the thing that would be gating and changing the different behaviors on a location by location basis. Now, the mechanism for all this, I don't really understand yet, but the basic idea. One thing, just if you're not aware of it, oops, let's see here. That's just repeating what I said earlier. This picture here shows a neuron in a dendrite, and one of the things we see often in real biological neurons is that when a neuron receives inputs from different sources, like I might receive input from one layer and it also receives input from another layer, or maybe receives input from the thalamus or something like that, they tend to be segregated on the dendritic branches. That is, they're not all mixed together. They'll be in some sort of order. The first from one source, the red source, then from the green source, and from the blue source. This has been documented in lots of different places, but I'm not sure it's been documented everywhere. But we do know this kind of thing does exist. And this is one way that this could work. For example, you might say, all right, I need to first, if red input may be coming from a state, and that just, in the blue input's coming from the feature, and the green input's coming from the location. Each of these have to be combined in a certain way that gates this whole.
Cut it off. I unwrapped it. We could keep it. Could throw it out.
You're unmuted. Well, you're talking about something else. I don't know.
I think that's Michael.
Sorry, guys.
Michael?
I was not on.
I'm sorry, Michael. I'm sorry.
Cat
sorry,
dilemmas.
Michael. Sorry, Will. I assumed it was Will. I was trying to do voice recognition. Anyway, there are mechanisms by which this occurs. So this is not a weird thing. In fact, our hypothesis and theory about how the thalamus does routing is based on this. And there's the same idea. And there's lots of evidence that it occurs in the thalamus. So this is not a crazy idea. I'm just pointing out it's like if you're thinking like, oh, these things, this input could gate the rest of it. And so you have to have the combination of all three of these things to get this neuron to be in a predicted state. Okay. Is that somewhat clear?
A quick question about that.
Yeah.
Wouldn't it be easier biologically to bind a state with a location if the sources did mix so that they could lie on the same compartment, dendritic compartment?
Say it again. I didn't follow that.
So I'm just thinking about, let's say we've got a dendritic compartment. It's got 20 synapses or something, and we need to get a certain threshold in order to get that neuron to fire.
Right.
So
yeah, go ahead.
It would seem like if you're trying to bind features, locations, or things from different domains together with a neuron, it would kind of, like, I'm not fighting with nature here. Nature does what nature does, but one would kind of think that it would be better to intermix your signals into so that they mix in dendritic compartments.
Well, maybe. I'm not sure why you think that, but let's just tell you why that might not work. Remember, for these, for example, let's say if the state was the red section there, right? This cell has to recognize the state. It has to say, oh, I recognize the state. That means it has to form 15 synapses or 20 synapses to the neurons in layer 2. If I intermix all these things together, then those 20 synapses may get far apart, and they may no longer be in a particular integration zone. That is, the integration zone is like, what, 40 microns wide? You might get 40 synapses in 40 microns, no more. So if I start spreading them out over a longer distance, then the neuron can no longer recognize the pattern in layer 2. It's just not possible because they're just spread out too far, and they need to be within some limited zone for that pattern to be recognized. So regardless of the merits of your idea from a theory point of view, and they might be great, I think from a mechanistic point of view, it probably wouldn't work. So
I guess in this case, Scott, do you mean like if it's sort of like an and relationship, like we want this neuron to be active if the feature and the state are there?
Right. So, we're just trying to bind together, say, location and state or something like that. Then we kind of want.
Because like dependent on both of them.
Oh, I see. Oh, I see. I misunderstood the question. The way I drew this, thank you, Niels. I think you're thinking like, oh, the neuron would fire if the red ones are active, if neurons fire with the green ones are active, if neurons fire with the blue ones are active. So when we want to bond together. Yeah, I guess that's what it looked like when I drew it like this. That's not what I meant. In some sense, remember that the way this actually works is there is a dendritic action potential that has to travel along the dendrite, in this case, from right to left. And that action potential could easily be blocked if the red pattern wasn't there. These are not just summed independently. They're in order, and the order matters. And so some of these could block the other ones. They're not independent. Am I getting at the question then?
I guess to your proposal, yeah. I mean, it seems true that, yeah, if it's learning the association of both the things, that could be learned in one compartment. I think was what you were saying, Scott.
Is that what you're saying, or are you saying that the red, green, and blue are independent?
Yeah, I was just kind of reflecting on the fact that let's say we do want the neuron to behave like a coincidence detector, sort of, but a coincidence between a particular location and a particular state. In that case, you would kind of prefer to have a single dendritic compartment to receive input from both location and state.
Well, maybe look at it this way. What if this neuron would only become, by the way, we're not even actually spiking, we're actually just depolarizing, but well, let's take that back. Let's say it's going to spike. That all three of these patterns have to be recognized. That the blue has to be recognized, the green has to be recognized, the red has to be recognized. And if they weren't all recognized, the dynamics of a dendrite are such that it appears that if they're not all activated, maybe even in the correct sequence, then nothing gets to the soma, or it doesn't happen. So the dendrite, that black bar, is not just a summer. it's a complex processing element, and the action potential on the dendrite the dendritic action potential has to travel along this distance, and it can be blocked along the way. I could go back and review it. There were several proposed mechanisms for how this works by other researchers, and it's part and parcel of our thalamus theory. That entire dendrite sections can be disabled by a particular pattern. Go ahead, Vivian.
Just sharing one neuroscience paper talking about this that I recently read and thought was really nice. This is in thalamocortical neurons, where it kind of shows how input from different sources like cortex, brainstem, TRN, synapse on different parts of the dendrite, and then they have like this whole theory around what kind of mechanisms this could enable.
Right. This segregation, like I've shown with the red, green, and the blue, that's seen lots of places. That this is not speculative. This is, and then the question is, what are the actual mechanisms that Vivian just mentioned, and how do they do things? There's a lot of complexity there. Some of it's not known, but I think for the moment we don't have to worry about that here. This may be important in the future. This may be some form of generalization, like you know, all the things that are recognized by the red or generalized, and all the things that, you know, there's could be other weird stuff going on here. All I wanted to point out that the idea that a neuron could fire or be depolarized based on the confluence of location and state, and then that those two have to be unique. There are mechanisms that would do this. It's not a crazy idea. In fact, it's not. It's almost like there's examples of it. So I don't think we need to worry about too much more than that. But it was a good observation. Well, you were right. I just didn't explain it completely. Are you okay with it now?
Yeah, I didn't want to derail too much. I was kind of.
Oh, that's Scott. I'm sorry,
Yeah.
Scott. I can't. I'm not looking at anybody, so I don't see what you're all saying.
Oh,
Okay.
Okay.
Sorry, Scott.
all good.
Where was I here? So again, going back to that other image, basically, as the location changes, sometimes the state will change, and I don't really understand that when it changes and how it changes. But if I have the correct state, given a state, given a location, it predicts a particular feature or no feature, and a different state at the same location would predict something else. And this is a mechanism for us to allow the model to have different predictions under different states of the
I guess
the object.
one thing I was interested in discussing about that was just because yeah, I definitely agree it makes sense to have the state be location specific in some of the representation or whatever for behavior. But like at the moment for like the kind of object IDs or the features are also location specific. And the way we do that is it's in the lower level column that we'd have a location, an object ID like in L3 that's
Are you
being
talking
fed
about
up.
you're talking about the child object ID?
Yeah,
Okay.
that's being fed up to L4. I'm just wondering, yeah, is there a reason you feel we wouldn't have something similar for state where it's like, yes, state is location specific, but the kind of handling of the location specific component is kind of delegated to the lower level column. So that any column is only concerned with it.
Following that. Explain it again to me. Like, should I
So
go
that,
back to this image?
sure.
So,
Yeah, so that I guess as well as the feature coming in, which is like if this is a higher level learning module, that's going to
yeah.
be the object ID from
Right.
L3 as well as
Right.
direct sensory input. But then it might also be getting the state of the low level object, the
Well, I thought
behavioral
about
state.
that. I thought about that. Should it be passing in the state? I don't think that works. But for example, I can imagine an object that has a lot of behaviors, and the child objects themselves have no behaviors. You know, the child objects are just, they don't have any behaviors. They would have no state to pass in. But the parent object would be different, have different states where it's expecting different child object in different locations. So we can come up with some examples of that. But that tells me that that I need to have a local state in the parent column, because it's not something that can be passed up from the child, because the child doesn't have any states.
I guess equally, like it feels like you can imagine objects that have behaviors that will kind of, when they are a child of a new object, they carry over those behaviors. So like a button can appear in different contexts, and whatever it's a child of, like a button has button-like behaviors. And then the high-level learning module that's learning like the compositional object needs to learn what effect the button has on the other child objects in its representation. But it doesn't need to relearn what like a button is. That's carried over from, like that's the responsibility of the lower level learning module.
Well, so I think maybe if I understood what you're saying, and I may not have, there's two things we're talking about there. How do I associate changes in state on different objects? Like if I push one button on an object, maybe another button elsewhere changes.
Yeah.
And it gets worse. I could push a button on one object, and completely different object that I'm not even attending to right now changes. You know, I flip the light switch in a room and a switch in a room and a door opens to the next room, you know, so, and we have, I'm going to talk about that because we have to learn those things. But I think that's a separate question than does a child object have to pass its state to the parent? Well, also, let me state this, Niels. I already stated that it's easy to prove that the column has to have its own state to tell how its model should change. I can prove that because the child object may not have any states, but the parent object can have behaviors. So there's nothing to pass from a child object. That doesn't mean that your proposal is wrong. It doesn't mean that we aren't passing state from a child to a parent at the same time. Maybe it is, maybe it isn't. I haven't really had a need to do that yet.Maybe I will have a need to it, but so far I haven't needed to do that. I need to have the state in the column. That I absolutely have to have, and I haven't needed to pass a state from a child yet. But I'm thinking about it right now. Maybe I will. I don't know. Maybe you can come up with some examples.
Yeah,
but
no worries. I just thought, I was interested to talk about, since we're talking about like location specific state. But,
right. I do think I can very likely prove that it has to be local, but doesn't mean it's only local. We might pass it as well. Like if layer 2 is, but I'll get to them in a moment. I do think states are things that have to be associated with across columns, across hierarchy, across modalities. That a change in state in one column could affect changes in state anywhere else in the cortex, in some sense. And those have to be associatively learned. I'll get to that in a second. Right, so we'll have to leave it as an open question whether state is actually passed in with feature.
Yeah, it seems like if you think, like, basically the state of the child object is kind of like another feature. So if we have the traffic light, the lower level might be just the light bulb of the green light, and that might be in the on or off state, like the light being on or off. And then that is just a feature that goes into the parent traffic light model. And when the traffic light actually changes its state from stop to go, the feature of the green bulb changes from on to off.
Right, but I also have to associate that with the changes to the red bulb and the yellow bulb. And those child objects are not necessarily talking to each other. But I would have all the information I need in the traffic light object. Yeah, I think for me, the way I would attack this problem is this was a very difficult problem we dealt with compositionality. And it took a long time for us to figure this out, that a parent object doesn't know what its child objects are. It just gets some bit pattern. That's all it knows. It's all it needs to know. It doesn't, in fact, it doesn't need to know where on the child object it is. It doesn't need to know the orientation of the child object. Well, maybe it does, but it certainly doesn't need to know the location of the child object. All it needs is the parent object says, oh, there's some bit pattern here. And I'm going to now back project to the person sending me that bit pattern saying, I'm at some location XYZ. You need to associate my location with all the details of your object, so your child object. So it could be that in the traffic light case, it's very similar in the sense that the child object doesn't have to send the extra information up to the parent object. It just the parent object projects back and says, "Oh, in this state, you should have been." I'm in this state in the traffic light. You should have been whatever state you were in the child object state.
Yeah, I guess just thinking that, like in the traffic light example, the high-level model that models the entire traffic light doesn't necessarily need to model how like each of the lights change on each of the, like how the color changes everywhere if it's on versus off. But the higher level model is used to coordinate how like the red light is on and then the orange light is on at the same time, and then those both turn off, and then the green light turns on.
Well, all right. So for it to do that, it has to have some sort of concept of state internally, so it knows where it is in that cycle, the order in which they occur.
Yeah,
Obviously,
so
the
that
But
red,
I
the
guess
red
wouldn't
light.
that be more like a global state, like or like that would be the state for the light as a whole.
Right. It would
I,
be, but it would be on a location by location basis. It still would be on a location by location basis because you can't have
yeah.
a state of a whole object. That we've already determined that there's no such thing as the state of a whole object. The object has many different things that could be changing.
Yeah, so that's what I mean. That's what consistent with everything I'm saying. I'm just saying that basically whether one of the lights is on or off is just a feature changing in L4, because like the fact that it is on or off is already detected by the lower level learning module.
Right.
And it's just a changing feature in L4, and how this feature can change and how the lights depend on each other. And the
Well,
temporal models and
imagine
what.
that we had a traffic light. What was this completely flat black? There were nothing identifying where the lights were. But then the lights would come on, and then there would be a red spot in this black area, and then there'd be a green spot, and then there'd be a yellow spot. But there is no other feature. If the light wasn't on at all, there'd be nothing to indicate there were any kind of things there. So essentially, it's hard to say that there's a child object at those locations where the lights are, because there's nothing physically there until the color changes. And then it seems to me there is no. I mean, then you might say, well, okay, there wasn't a child object, but now there is a child object, and the child object is green circle. That, I guess you could model it that way, but that still, my point was, there'd be the child object wouldn't be sending up a state. The child object would be either it's a green circle or it's not a green. It's either there's a green circle or there's no green circle. It wasn't like there was a green light, now it's off. It's just like a moment ago there was no green circle here, now there is a green circle here.
Yeah,
and so
I guess I was just proposing that basically whether the light is on or off, which could be the state of the lower model, can be treated the exact same way as all the other features that come in. Like there is a green circle or there's not a green circle.
Right.
There is a bright light and there's a dim light. There's a non off
well,
light.
I would agree with that. But I guess the question we're going back to what Niels is asking about, whether we're passing state into the parent column.
Yeah, so that would be arguing we're doing both. We have the state in L2, like you suggested, but we can also receive the state of a lower level of a child object as a feature and interpret it as a feature in L4.
Okay, the language gets a little confusing. I'm open to these ideas. I guess what I'm going to be adamant about is that there is a local state to the column in the model, and that state can change on that state represents the state of the current location and not anything else. And it has to be local. Whether we're also passing in state from a child object, I'm open to that. I think it's, it seems like a possibility. But it is confusing to think about, like, exactly what's required. So again, maybe we can leave that as an open question. We could say, in this thing here, we might say something like, how about that? Will that address our confusion for the moment?
Yeah, and basically it wouldn't be treated any differently than the features that are coming in. And it wouldn't be equivalent to the state that's being modeled in L2 or whatever layer.
Well, if we're passing in state, if it's a separate variable, I assume it would be handled separately somehow. Would it, or is it just the feature and the state are combined?
I'm not sure. I mean, I would argue it could be treated the same way as other features that are coming in, but.
Well, then it's, so from the column's point of view, it doesn't, you're saying there's not really two things. It's just feature and state.
Yeah, the state becomes another feature at that location.
Okay. Well, I'm open to all these ideas. I find it a little bit confusing to think about. Maybe some, clearer examples will help tease apart these issues. One thing that the state has to do, which I'll come to in a second, the state labeled in this picture, it has to associate a link to other states. It has the associative link between changing states within this column, like a change in one part of an object would lead to a change in another part of an object. Or it could lead, a change in this object could lead to a change in state in a different part of the world, a different object. And those links have to, those are sequential associative links and that's not the same as voting, right? That's more like a sequence. So
yeah, it feels similar to like how features change based on movement.
Based on movement or based on anything, really. It's just we have to, we have the whole trick here, the bottom line of this whole thing is to causally relate changes in one thing to changes in another thing. That's how we learn to use tools or turn on things or manipulate stuff, right? How do you change one thing to create a change, a desire, or change somewhere else? And so the state variable, wherever it is going to be socially linked within its own column. So, for example, if this was a traffic light, or modeling a traffic light here, imagine that imagine you're looking at the traffic light through a straw, okay? And you can't see the whole traffic light at once. And you're looking at some benign part of the traffic light, and all of a sudden the light comes on. Well, as we talked about in previous leaks, some external action policy detects there's been a change. The column moves to that change and says, oh, there's a green light here. And it says, the last time I hear, there wasn't a green light. So my model says there was no green light on at this location. Now it's green. So it says, okay, something has changed. This is a new state at this location. Then the yellow light turns on and the column is once again redirected to the place where that change occurred. And the same column says, oh, now at this location, I was just looking at the green light. I was a state. Now we're in this new yellow state at this location. So I can link basically the pattern in L2. At one moment represents the green light came on in one location on the object. And the next moment it represents the yellow light came on in another moment, point in the object. And you can associatively link those two. It says, okay, well, when the green light was followed by the yellow light. Because this column literally went from the location of the green light to the location of the yellow light as they changed. And so you could follow through this, and the single column would learn that this is the sequence that when I see the green light, then it's followed by the yellow light, and it could expect that, and it's followed by the red light, and so on. It could also learn the timing of this, meaning if maybe there's a 2-second delay in the yellow light or something like that. So you can imagine now this changing in the state variable over time represents the different object behaviors of how an object changes over time, and it can learn that. And then we could say, oh, well, maybe when the green light comes on, a bell rings, and so there's some other column in the cortex, in the auditory cortex, that it's jumped into like, oh, I'm listening. The bell just came on, so a change occurred, and there would have to be a link between the green light in one column and the bell changing in another column. But that would be easy to do. It's just another association if the connections could be made. So I think this is a way of like tying these events together. So these associations of states within a column and between columns is how we would learn how objects behave over time. Did that follow? Did everyone follow that?
Yeah, that was really helpful.
Now I'm going to make it complicated. Let's talk about the stapler top opening. The problem with the stapler top opening, imagine I'm watching through a straw. There's a lot of things moving. It's not just like the green light. Okay, there's one point where there's a point in space where the green light came on. I'll go to it. But the stapler top is moving. There's multiple things that are moving at once. So imagine you're looking through a straw at the bottom of the stapler, and now the top starts moving, and a detection is made. Well, the column can only jump to one new location, even though there are many locations changing. Like all the locations along the stapler top are moving. Where does that column go, and how does it learn that all those locations are moving at once? I don't know the answer to that question yet. So, that's introducing a potential problem. I just throw it out because it's like, okay, I got the traffic light. That's pretty easy. Pavlov's dog. That's pretty easy. But stapler top. That's a whole bunch of positions changing at once. In the space of this object.
I had that question written down, like if multiple things change at once, how is it that the column doesn't re-anchor and say, oh, this is a completely different thing now.
Well,
lots of stuff is changing.
It's kind of trying not to re-anchor. Typically you wouldn't re-anchor. If something just changes in the world, something you're looking at, you wouldn't think it's a new object. You just think like, oh, this object I'm looking at is undergoing some transformation. So I'm not worried about that, but I am worried about the issue of like many things happening at once. Imagine I had a toy and there was a button on the toy and I pressed the button on the toy and then 10 different things on different locations on this toy changed. You pushed it and then a little window opened up at one place and you pushed the button at the same time, a little wheel spun, or at the same time the light would come on, at the same time a sound would come out. All these things let's keep it all visual. There's different things that are visually changing about this object. Now, when you first experience it, now you're trying to learn this, right? You can't learn all those things at once. It's impossible. You can't attend to all the different changes at once. What you would tend to do is you do it over and over again. I have lots of little grandkids now, so I go see them doing this. They'll push the button and they'll focus on one thing that might be changing, and then a moment later they push the button and they focus on another thing that might be changing. And so you can't absorb all these changes at once. The straw can only look at one thing at a time and say, okay, well, how's that change when I push the button? How's that change when I push the button? I push the button, see it change. Push the button, see it change. Push the button, see it change. And then I'll say, push the button, watch a different change someplace else. And somehow we bring all those two together. I think it's going to work. I think it actually will work. But I have to walk through the mechanisms to see how it would work. But you can't learn it all at once. You'd have to learn it sequentially. Once you've learned it, then I push the button and I would have I can have an expectation about any one of those changes that would be occurring. I say, well, if I push this button, I know that over here, this will change, and over there, this will change, and over there, this will change. But I think you have to learn them sequentially from repetitive practice.
One thing I'm not saying this like is a perfect solution or something, but one thing we've talked about, I guess, is like how with hierarchy, if the stapler top is kind of a child object, it's easier to imagine how that's represented with a kind of single representation.
Right.
And I think one thing, Vivian, you talked about on Slack at one point was how like you can imagine if you can vote on a state or sorry, let's say a ID and pose, and you can do that quickly enough to kind of infer it, that makes it easier to learn a behavior. So as in the connection here would be like, as the stapler top opens, because all the columns that are the kind of straw worlds looking at the stapler are seeing a consistent pose and orientation of the top, they agree on the pose on the top. So we quickly determine like, okay, this is the new state, this is the new, or like this is the new pose of the thing. But someone dancing or like this complex toy, to your point, is going to be harder because like each arm and each leg is going to be kind of like they're basically creating like a totally new thing, and we need to like break it down and learn that this is like a new
right. Like first, like, okay, how do I move my feet? Then how do I move my hands? And how do I move my this and that? Well, the thing about the stapler top, which is interesting, and it's a compelling idea that maybe the whole top is like its own child object, and it may well be that way, but it wouldn't start out that way. I can easily imagine an object like the stapler where I have no idea that it's about to move, or that it even has a seam or a hinge or anything. And so I learn a model of it. And that model does not have like, oh, the top part is an independent child. It's just, there's no evidence that I can't possibly imagine that. So I've learned this object, and so there is no child object which says top of stapler or top of box or whatever it is. And now it starts moving. So the first thing that there is no child that I can say, oh, this whole child is moving. So basically multiple points on the object are changing at once. Maybe through practice, I'll learn that the top is a separate object. And maybe that's the right thing to do, but initially it wouldn't be that case. Initially, I would have an object that you just imagine it's a rectangular box. There's no seam. I don't know anything about it. And now all of a sudden the top opens separate from the bottom. So I didn't have a model at the top separate from the rest of the box. There was no visible evidence for that. Now, what do I do then? Maybe what you're suggesting is maybe then when I first see this thing happening, maybe I just start focusing on and learning a new model of the top. That's the first thing I do. So imagine looking through a straw, and I'm looking at the box, and then the box changes, the lid opens up, and then my straw is redirected to the point where the lid, somewhere along the lid, it's now partially up. At that point, I say, this is different. But maybe what I would do then is then scan along that lid and say, okay, this is a separate object, and I'll form a child and something like that. But it's complicated. It's not so simple. I can't always assume that there's a child object that's changing.
Right.
I kind of like the idea that I think you wrote in your write-up, or maybe I misunderstood it, but basically that in layer 2 or wherever the state is being modeled, we can learn associative connections between states. So essentially, if I'm detecting, all right, the top of the stapler is in this state, I expect every other point on the top of the stapler to be on a certain state. Like I can...
But I have to observe that, right? I can't assume that. I have to observe it.
Yeah, and then, yeah, tying into that would then be that, yes, we would have to learn that once, and it would be pretty tedious to learn that, but then we should be able to transfer that onto other objects, basically solid lines moving in this kind of stapler
right
type way. So we wouldn't have to relearn it every time.
I agree with that too.
Lots of objects.
Right. Although I can come up with all kinds of screwy, examples that make our life a little bit harder. Maybe, so we talked about like making the stapler more like a box, and you're just lifting the lid of the box. Well, what if the lid of the box was hinged on both ends, and it lifted up in the middle, like you had two pieces opening up? Well, that's a different thing. So I have to be able to learn all these, right? I have to be able to say, okay, how many, and I wouldn't know that, by the way. I couldn't know that until imagine your straw visual system. It could go up and see the right side of the lid going up, and you might say, oh, the whole lid is going up, but it wouldn't be, because the left side would be going in a different direction. And so it's sort of like, it just kind of proves that the system has to observe all these different parts. It has to go around and try to figure out what has moved and where it's moving. And the straw example gets really hard because there's multiple things moving at once. And by the time you get to see where the other things, they've already changed. You know what I'm saying? It's like, you can't, everything's moving. So if it's just one thing was changing, you could observe it. But since multiple things are changing, it drives you crazy. It's like, where should I go? And how do I observe? And how do I know what happened in between? Anyway, I'm riffing on what you said, but mostly I'm saying it's a challenge to understand how, like, the single column would learn. How could it learn all the complexities of a complex behavior? The traffic light is a simple behavior; it's easy to understand. But an object that has multiple things moving at once, it's difficult. And we can't assume that there's already child objects and only the child objects are changing. So somehow the system has to learn this. And you can just imagine looking through a straw and trying to do this. Like if I was looking at an object and I didn't know it had any behaviors, and then something moves and my straw is redirected up, but I'm only seeing part of it. And then something else is moving, and I can't see everything that's going on at once. It would be very confusing. I wouldn't be able to figure it out. So I'm not sure how it happens. Anyway, I'm almost done here. I know if we got 15 minutes more of time here. Let me go back to my text slide, if that's okay. I'm going to stick with the object behaviors and learned by location on location basis. We're open to the idea that that state could be passed in from a child object, as we talked. I'm going to jump down this paragraph here. Oh gosh, I needed that. It's a little fact. If you didn't know this, it's interesting to know. On layer 4 cells, these are the cells that get the input directly from the retina. Less than 10% of the synapses on those cells are actually coming from the retina. So people say, oh yeah, layer 4 is driven by the retina. It's like 7% of the synapses are coming from the retina. About 40% come from L6, which is consistent with L6 being the location, right? And then, but that leaves about 50% unaccounted for. So that could be state, just won't pass that on in case you didn't know that fact. And then the stuff I talked about just a moment ago. I said behaviors are association of state changes. So when we talk about a behavior in an object, we're referring to a set of state changes that are causally linked. Something changes here. It could be one thing, it just changed by itself. An object could one moment be green and the next moment be red. But typically, something happens one place and something happens another place, especially if it's something that I had to do, something I had to manipulate. So most object behaviors consist of multiple changes to the object. These changes can occur simultaneously at multiple locations. For example, simultaneously at multiple locations would be like the lid of the stapler going up. Or another example is a switch might turn on lights at multiple locations, and you have to learn each one. Again, if you're looking at the world through a straw, you wouldn't be able to see those multiple lights at the same time. You'd have to do them sequentially. And sometimes these changes occur in sequence. Like the top of the stapler is a sequence. It doesn't jump around. It goes in and flows in a sequence until as the sequence goes up. And then I mentioned here too, like if the stapler deflection plate rotated as the stapler top was raised, so you'd be raising the stapler top, but something else would be changing it elsewhere on the object. And a single column can't learn all this at once. It'd have to learn it through multiple repetitions of the behavior.
It also feels like another kind of key part of like the conditional transition or whatever in the states is actions, and like, yeah, I don't know whether that's represented in L5 or whatever, like somewhere that would probably play in terms of like, how are we moving through the state space of the stapler? Well, it depends on where we're pushing on it, or things like that.
I've been kind of avoiding that difficult problem for a moment. But you could imagine if it's a button, I could at least say, well, I don't have to worry yet who pushed the button. I could just say the button went down and the top opened, I'll come back later and say like, okay, how did the button get pressed? How did the button go down? And of course, it's complicated by things like capacitive buttons where they don't move at all. It's touch an area and something happens. It's a good question, but I think that's an extension of this basic theory. At least I'm hoping it is, Niels. I hope everything I've described so far is consistent and doesn't have to be changed, and we can then add on like how did the button get pressed? And that would be the ideal thing. So we were just talking about how we learn these changes in states. And I'll just read through some of these. Comments here. I say a column must be able to learn behaviors of objects. It needs to learn which changes occur together and how these changes occur sequentially at time. And the basic method would be learning associations between the SDRs and the state layer. And a change of state in one location would be associated with a change in state in another location. So that all hangs together really, really well, I think. And then I say a state and location for location A can be associated with a link to a state in L2 for location B. Again, so if I know that something happened in A, and then layer 2 would predict another state, that new state would be specifically linked to a different location. So this tells me that states are tied to locations. If I know the state of something is changing, I know where it's changing, and I could direct my attention to that point. So it's like if I go to that location, I know what will be there. I said the learned associations L2 can be one-to-one or many-to-many. This gets back to the idea we were just talking about, like simple thing could be you push a button, the light comes on, but you lift the stapler, multiple things could be happening at once. And so it could be, many things are associated with changes. Many changes can be happening at the same time. And these changes can be sequenced, or they don't have to be sequenced. I can push a button and instantly everything changes, or I can push a button and there's like an order in which the changes occur. And then some of those sequences could be learned with or without timed intervals. So a traffic light is a sequence, but it doesn't. Well, I shouldn't use the traffic light because there are timed intervals there. Well, these are both timed. I think I get the wrong examples here. Anyway, is this garbage? This, I think, look, I messed up some of my text here, I think. Let me just look at this one here. All right, that was repetitive. I think I meant to remove that paragraph. I talked about this earlier. We talked about single column will automatically learn associations between the states of that object that's being modeled by that column. But if multiple columns are simultaneously serving the same object at different locations, so imagine I have multiple columns looking at the stapler now at the same time, multiple columns, multiple patches of the retina. Then the long-range connections between layer 2 will associate changes occurring across columns. So I was trying to get at the fact like, okay, well, what if I didn't just have one column? I wasn't just looking through a straw. What if I had multiple columns observing different locations on the stapler at once? And they're all observing different, some of them are observing changes and some of them aren't. But the ones that are observing changes could link to the other ones that are observing changes at that moment in time. So this is a little complicated, but imagine my eye is fixated at one point and the lid of the stapler is rotating up. Well, there'll be a whole bunch of columns that were observing the stapler top that then don't observe the stapler top. And then a bunch of other columns that weren't observing any part of the stapler that are now observing part of the stapler. And so a whole bunch of columns would be going through state changes simultaneously, but they could all be linked. So they're socially linked. So, the change anywhere could predict a change anywhere else. And this may be the way of dealing with the fact. This may be one way of dealing with the fact that maybe the top of the stapler is not a separate child object. I need to learn all these things at once. I don't know. This is just an observation. What would happen if you had multiple columns observing the stapler at once? That many of these columns would be observing behaviors and state changes, and they would be linked, and those links would all make sense. They'd all sort of associate somehow, and I don't really understand it yet. So this work across
would this be like voting on states?
I don't. It's kind of voting, but I don't think voting is the right term for it. I thought about that. I said, is this voting? And I didn't spend too much time thinking about it. I said, well, it doesn't feel like voting is trying to reach a consensus. And these might be voting. I mean, I don't know. It's a great question, Vivian. Maybe we should just leave it unanswered. It feels like voting, but it feels like it's doing something more than voting. In my mind, voting was like, okay, we're trying to reach a consensus on a thing. What is this? Is it A or B? This is more like voting about what should happen next. All these people are saying, yeah, I see what's happening here. And then one says, I'm seeing what's happening here. And there's sequence to it. Another thing is, by the way, these are all sequential. The time is important here, right? The order in which these things occur is essential, whereas in voting, it doesn't seem to be essential. So they're all sort of, everyone's voting on what the next thing everyone should see. That would be, then it would be voting. Yeah, right.
Yeah, so it's in a sense like voting that it's associative long-range connections.
Right.
But yeah, maybe a bit more of a temporal dimension than when we're voting on.
Well, it has definitely an order to it, right?
Yeah.
The order is essential. Things can happen at the same time or things can happen sequentially, but they can't happen backwards. If B usually follows A, then I don't expect A to B. Well, B might predict the state of A, but it wouldn't predict that A is going to change. It's an interesting question. I even asked myself this question at one point. I remember now. I said, hey, could this be all the voting? Could all the voting be done like this? So somehow it seemed like voting. So maybe this is how voting occurs. And I got confused. I just was, my brain was getting fried thinking about this stuff. And there's only two more or less points on this page. I've already mentioned that behaviors, you can associate behaviors across modalities. That's easy. It's any layer 2 cell changes, another layer 2 cell changes, and you can associate them. And then the last thing here is it wasn't even clear if I have the state variable, what does it default to, and what does it change to, and does it have meaning? Like Niels and Rami have been talking about. and how is a new variable chosen when a change occurs? I don't have any answers to any of these questions. I just was like, oh, I don't really understand this. So it's like, well, it's not complete yet. So I'm done. I'm just say I feel really good about this stuff. I feel like, again, as I've said in the past, I'm making progress on this. So that feels great. Clarity is coming is showing up, which feels great. Even though there's many things that are still unclear, the only thing that's important to me is that it feels like we've nailed down a few concrete items, and then we can go on from them, and much better understanding what's going on. So that's where I am. I'm done.
Nice. Yeah, Hoj, did you have a
yeah. I guess I was like thinking about the question that Jeff had at the end, and also think it relates back to the question that Vivian asked in like in the middle, like is state part of features? And I wanted to like I just thought of like another way to think about it. I just want to like share I guess on my screen probably the easiest. So like we're talking about like features, and then depending on the lower level, we might have pose, color. Higher level might have ID. Um, and of course, they're in some kind of location. Let me just put that as well.
So are you saying the features consists of pose, color, and ID, or is that what you're saying? The features consist of those things, or those separate things?
When we talk about features at location, we're talking about all of these in the same location. Like
Okay,
we are
so
sensing all of
what you're
these.
saying, the word feature is composed of pose, color, ID.
Yeah, let's think about this as like I guess I like to think about it as like a dictionary or a set of like things that we are uncleanly sensing. And then so if we think about state as like part of features, and I guess I would add that here, right? This would be, whatever we call, S1 state. But then I think another way to think about it is actually kind of, let me try to delete this, is to think about it as kind of as like a whole thing is a state of itself. So, and this is not exactly clear, so I'm going to go in, like, I'm going to explain it a little bit more. So, when the learning setting, we're at an object, we don't know what the state is, like, we don't know what the variable is. So we just, call it, at least in program, let's just call it S1. So like, and then, this could be part of an object that never changes, sometimes changes, whatever. And then later it comes back to the same location, but then this time it notices like a different set of features. Is there a way to move this? Yeah, no. So like okay, in a new visit, the second visit, we have some features, but now color is, let's say, initial color was, I don't know, green.
We're at the same location. It just now
Yes,
come
we're
back
at the
to.
same location. Yes, because
Okay.
I'm in the same location box. So now this thing has changed to red. So now, it's like, okay, like here, now it came back and now like, so the feature has changed. So I'm gonna like say that this is, oops, I'm gonna say that this is like another state. So and I'm gonna call this state two. And so like the location like would store states, and I think this is in line with the fact that, okay, like the states are tied to the location. And it's just that at that particular location, the feature sets like have changed. So like maybe, I don't know, they could be like a location plus like a particular feature set, maybe. Um, yeah, I guess so. Instead of thinking of basically, I mean, the conclusion is like instead of thinking of state as features, maybe we can think about it this way. And I think this still is aligned with everything.
I'm confused. Is this different than I proposed? I'm a little confused.
It's the same, yeah. No, it's just
Okay.
yeah, it's just I'm just trying to clarify like where state might be residing. Like is it part of features or is it like Yeah.
So
So it's just a very
this is
different
the
case.
question: is a state associated with a location, or is it a state associated with a feature? Is that what you're asking about?
Yeah. So
Uh-huh.
I mean, state is definitely. I mean, I agree with you definitely that, or I'm convinced that state is dependent on the location. And I guess if this is more programmatically whether we define state as like part of features and therefore it gets um, sent to higher level things, or whether we define state just another way of defining state in the implementation terms. Anyways,
Yeah, no, I
yeah,
mean, I think it kind of gets to the semantics of like how we refer to state, and maybe also like the point Jeff was raising that it can be a bit confusing how the term quickly gets overloaded.
yeah,
And like Vivian was also, because this is actually kind of how a state is defined in the code base at the moment. There's like this state object
yeah,
that
yeah,
you may have seen, and
yeah,
um, but then we talk about like behavioral state like on or something like that, or like a behavioral state like you know, I don't know, crushed, open, whatever. Uh, and
yeah.
so, yeah, I guess we need to somehow find a language that enables us to, um, yeah, talk about it in a way that we don't get too confused.
Yeah, maybe in code we can just change the state to CMP. I don't know. Yeah. Um,
Well,
Yeah,
obviously, what we actually call things is not essential. It's very helpful to pick good words,
yeah,
but we have to agree on the principles. Right? What do we mean by it? Right? That's the most important thing.
yeah,
Um, I mean, some really good ideas came up here. I mean, I think it's worth thinking about further the child-parent relationship and whether state can be passed in that way, or what does it mean? It's consistent still to say, oh, there's a state variable on an object location basis, and also maybe that's passed on to the parent. It's not clear yet to me. Anyway.
Yeah, I feel like this was at least the most coherent view of modeling object behaviors we had so far at the end of a research meeting. So
Oh, wow. I guess that feels like it's not saying much.
well, we're
I'm like,
making
man,
progress, is what I'm
I,
saying, I guess.
I think so too. I've been through this so many times that it starts out this really muddled confusion, and then you slowly pick away at it. And I recognize this. I recognize this process, and it's like, oh, this is going to work. We're going to get this. So I feel really good about it. Yeah, a lot of
nice.
clarity. A lot of clarity came along. Well, I'm going to continue working on this primarily anytime I have. Maybe next week I'll have some more things. I'll see. I don't know. All right. We got
Great.
anything
Yeah, I
else?
think that's
Anything else
everything.
to say?